The small data set that we're looking at for this introduction to matched pair studies has to do with an insurance fraud investigation for Jocko's Garage. So you can see from the data and from the description that we had 10 damaged cars. We sent each car to Jocko's Garage into another garage and collected estimates. So let's look at the difference for each of these cars. And we'll go Jocko's minus other. So we've got $100 for number 1, $50 for number 2, negative 50. We got to stay consistent with our order of subtraction. And for car number 4, they are both the same, so that difference is 0. Back to negative 50, 200, 250, 200, 150, and 300. To address the question of whether prices charged by Jocko's are higher than those at other garages, we might start with the hypotheses. H0, the mean at Jocko's, is equal to the mean at other garages. And HA, our alternative hypothesis, is that the mean at Jocko's is higher, or is greater than, the mean at other garages. This is mu sub O, not mu naught, since what we're actually looking at is a comparison between two different parameters. Now, we can tell by looking at these numbers here for the differences that it does look like most of the time the Jocko's estimate is higher. There are 2 cases where it's lower and 1 case where it's the same, but all of the bigger numbers, the numbers that are farther from 0, are positive. So based on that, we can tell that this sample statistic here being positive, this must be subtracting Jocko's minus other, and therefore this randomization dot plot here must be for Jocko's minus other. So this is x bar sub Jocko's minus x bar sub other. And because of that, we want a right tail test, because we would want mu sub Jocko's minus mu sub other greater than 0. So we'd take a right tail. And we can see from this graph here that that right tail is already highlighted, and we have a p-value of 0.329. Now, a p-value of 0.329 gives us absolutely no statistically significant evidence against the null hypothesis. So this conclusion would suggest that based on these numbers, we have no evidence that Jocko's is charging more on average than other garages. But if we look at this list of differences, that doesn't seem all that plausible. Almost all of these are positive, and we have a lot of fairly large positive numbers in here too, with only a few of them being close to 0 or negative. So that alone is enough to make us question this result just a little bit. Well, it turns out if we're doing this hypothesis test based on a randomization dot plot of x1 bar minus x2 bar, then that means we're treating this as 2 independent samples. What that would mean is that we took any 10 damaged cars to Jocko's Garage and got a list of estimates. Then we took a totally different random sample of 10 damaged cars and took them to another garage. So there's a lot more room for variation in how much damage was actually in those cars in the first place. So this is not the correct, 2 independent samples. This is not the correct way to model this situation, because we can actually eliminate a lot of that variability by taking advantage of the fact that we know they were the same cars. So it was the same damage that we were getting 2 different estimates on. It wasn't just any old 2 cars that have been in an accident. So the correct way to actually model this is just doing inference on one mean using this data set of differences. And inference for one mean on that data set of differences is what we have in this next graph here. So notice that this is now a randomization dot plot of x bar, just a single x bar. That is the mean of the differences instead of the difference of the means. In calculating a single value, it doesn't matter whether you take the differences and then average them, or you average and then take the differences. You'll still get the same number for that one sample statistic, but it makes a big difference in the variation of the sampling distribution, because this sampling distribution is resampling from the sample of differences. So from the variable difference, instead of resampling from both of those lists individually. And here we could write our hypotheses the same way, but when we're working with really one variable, it's a little bit better to let it all be written in terms of one parameter also. So that's where we start to write this mean as mu sub d, the mean of the differences. So our null hypothesis is that the mean of the differences is 0, and our alternative hypothesis is that the mean of the differences is greater than 0, noting again that we are sure that we're subtracting Jocko's minus other because this sample statistic is positive. We do need to really be careful and make sure we know the order of subtraction if we have a one-sided test. We can see in this distribution that our p-value is 0.002, a really dramatically different p-value from what we saw in the other model. So this actually gives us very strong evidence against the null hypothesis, and therefore very strong evidence that Jocko's charges on average more. So we can see there were two ways to approach this, but they're not both equally valid. Once we know that we have a matched pair study, which we can recognize here based on the fact that they were the same car, it wasn't two totally independent samples of cars that were sent to the two garages, we know that, in fact, this first approach is incorrect, and this second approach is the right one.